What's up, YouTube? Welcome back to another day practicing abstract algebra. In particular, we are studying representation theory of finite groups, working out of this book by Benjamin Steinberg. This is an excellent book, and we've always been just calling this week graduate level math week, algebra, but now I'm starting to think of it as algebra week. So the primary focus, the primary book this week is this book, but really I am going to be pulling material from all of my algebra books. There are half of them off of the camera right now. So some of these are going to be more undergraduate level, things like linear algebra. Some of them might even be more high school level, like this challenging problems in high school algebra. Some of them are going to be graduate level, scary books like these top ones. But the primary goal, the primary focus is representation theory. This is the study of symmetry using linear algebra, the study of finite groups, which in some sense really capture symmetry and describe symmetries of objects. Hey, what's up? We got somebody in the chat already. How's it going, dude? What's up? Bit of Hope. How are you? I need to get the iPad up. I forgot I forgot to get the iPad on screen. So, let's go. I hope y'all are having a good day. I am joined, as always, by my beautiful cat, Luna, and hopefully she'll be making an appearance as we start practicing. So, welcome everyone. Yesterday, we made some really awesome progress. I hit a major milestone for me. For me, this is a major milestone. We got to Maschke's theorem, the end of chapter 3. For the first time on this channel, I got to the end of chapter 3 on the introduction to group representations. So, dude, I'm stoked. Today we may start chapter 4. Hey, Luna! Oh, she had trouble jumping. Luna, how come you can't jump? Come on, dude. Come on, dude. Oh, she didn't know that there was going to be a stack of books, I think. I think that's why. Oh, Luna. Hi, baby. So, welcome everyone. I'm joined by my beautiful kitty cat, Luna, and she's going to be my math practice buddy today. How's it going, Bit of Hope? I hope you're doing well. Okay, so I'm getting my iPad on screen. I think we're good to go now. Yeah, we got the iPad. Okay, so as I said yesterday, for the first time, we got to Maschke's theorem. And this is a major result in the representation theory of finite groups. It's kind of the equivalent of prime factorization, that any number can be uniquely factorized into a product of primes. Primes are like irreducible numbers. And then this is saying that every representation can be uniquely factorized. I believe uniquely, doesn't say unique, but that every representation can be completely reduced. Hey, may you please advise me on how I can clear my maths basics being a high school student? Follow my basic math course. Naima, do you know about my basic math series? Let's see. Follow my basic math videos. A shortcut for this is mathcanbeahobby.com. So there's a playlist. And I'm going to pin this message so everybody can find that. All right. Great. So let's get started. Maschke's theorem. I remember working this yesterday. So today I want to begin with an exercise. Can I work an exercise? Yeah, Naima, have you seen those yet? Like, especially the first one is going it's settling. It is settling. It's no longer accelerating and going super, super viral, but it's landing at 200,000 views. 200,000 views of people announcing that I'm starting. 200,000 views of people watching me announce a new mathematics series. That's pretty incredible, I think. I'm very, very proud of that. Okay. Look at the kitty cat. Okay, so I've done exercises 1 and 2. I don't really feel like reworking exercise 2, even though I don't think I've ever done it on stream. Let's begin with exercise 3.3. From Steinberg. This one says, let phi and psi be representations of, be one-dimensional representations into the one-dimensional complex numbers. So be one show that phi is equivalent to psi if and only if phi equals psi. Cool. I think it's pretty clear that if two representations are equal, then they are equivalent. So I think the only interesting part is if they are not equal, to show that they are not equivalent. Or vice versa. If they're not equivalent, then they're not equal. So clearly, if phi equals psi, phi is similar to psi. Thus, it remains to show that if phi is similar or is equivalent to psi, then phi equals psi. So, by the definition of equivalence, there exists a linear transformation T, which is an isomorphism from V to W, such that this diagram commutes. For any group element, we have this commutative diagram. Phi G and psi G, such that this diagram commutes. In our case, the vector space is the complex numbers. So, because C star is isomorphic to GL1 of C, which is isomorphic to GLC, we can take V is the complex numbers and W is the complex numbers. So there exists a transformation from the complex numbers into the complex numbers which is an isomorphism. Any such isomorphism Hey, Abuskayed, how are you? Good to see you, man. Good to see you. Dude, thank you for joining as a channel member, my friend. Thank you. It really means a lot. Luna, do not knock down the... Do not do it. Or Kayed, right? Do I pronounce it Kayed? Well, thank you, bro. I don't know. Let's see. Yeah, dude. Good to see you. Any such isomorphism is multiplication by a complex number, I believe. Let's call it Z naught so that any complex number is mapped to a multiple of the complex number. Where Z naught is not equal to 0. I don't love Z naught not equal to 0 because that it looks like Z0 not equal to 0 and we've got a lot of Z's. What if we get fancy and say zeta? How do I write zeta again? How the hell do you draw zeta? Zeta fixes a single Z in a different writing system, right? Zeta symbol. That was close. Ah, yes. It's like this. That's right. Okay, so this complex number is fixed. Dude, let's not do that. Let's just use alpha. And alpha needs to be non-zero. Okay. Or capital Z. Capital Z would be maybe nice too. I need to double check this, but I'm pretty sure that this is true. I believe that any isomorphism of the complex numbers to itself, it has to be multiplication by a non-zero complex number. Thus, because phi is similar to psi, for any group element, then this diagram commutes, which means that psi after t equals t after phi. So, in other words, psi equals t phi t inverse. And because t is multiplication by a complex number, then first let's write the statement for a specific point, z, for a specific number. And now we know that we have this. Phi g is note that phi g is multiplication by some non-zero complex number. Or at least it is... Wait. Dude, I want to say... Oh, wait. Phi is a linear transformation. It is a linear transformation of complex numbers. So phi times k z, we can factor out scalars. So I can factor out the complex scalar alpha inverse. And alpha inverse, invert to 1. So, psi z equals phi z for any group element and any point in the complex numbers. Therefore, psi equals phi. And we are done. There's nothing left to prove. And we are done. Dude, I think that this is correct. I think that this is fully correct. I should say any such isomorphism is multiplication by a non-zero complex number. I did say it after. I said where alpha is not zero. I do have this to do. I'm pretty sure that this has been an exercise in the past. I think that this is an exercise. In particular, this follows from the fact that we say GL1C is isomorphic to C star, the multiplicative group of complex numbers. Pretty sure that this is true. And I can cite this statement on page. I mean, we use it everywhere, but on page 4, GL1C is isomorphic to C star. Any linear transformation of complex scalars I think, yeah, we need to. Like, in particular, we can then take T of 1 is some image of the identity element. Yeah. Yeah. So therefore, T of any z, if we are working over complex, the vector space being the complex numbers and the scalars being the complex numbers, I can factor out z. So it's any linear transformation is fully determined by its action on the identity element. So I'm pretty convinced that alpha is whatever T maps the identity to. And as long as that is non-zero, then we have built an isomorphism. I feel pretty good about this one. What's up, the math maestro? How's it going, dude? How are you? Y'all, I should... Dude. The math maestro. A helpful book for... What is CP? That sounds inappropriate. Y'all, be right back. I gotta pee really quick. BRB. back. What's up, everybody? Yo, Prashul Kaushik, dude, I'm glad that you enjoyed it. I'm glad that you enjoyed it, man. I'm proud of those videos. Keep an eye out for the later ones. I just released episode 4 just yesterday. So, man, yeah, I'm very excited for that series. I think I really think it's got potential for me. Like I would love to just keep making those videos because I get to share something I'm very passionate about that I love very much, proof-based abstract mathematics, but really not necessarily abstract mathematics, but math done the right way, I guess. Like, get an opportunity to teach people what real math looks like, which to me means number theory. Like, let's teach people number theory and tell them this is how you should have learned math. We should have reset and kept coming back to addition and multiplication and stick with the whole numbers. We should have been teaching number theory all along. I think that's true. I really do. I think that we should have had way more number theory, much more number theory in high school math. So, dude, I'm glad you enjoyed it because that is truly a number theory fact. Like, the sum of the first n integers is n times n plus 1 divided by 2. That is a number theory. That's a number theory fact. That's straight up number theory, and it's beautiful. It's just so nice. It's so simple, and people enjoy it. Like, dude, I feel so strongly about this that we would improve math education in the US and probably everywhere. I don't know about other countries, but in the US we would benefit by teaching more number theory to kids. Yeah. And somebody might say, "Oh, but that math is useless." And it's like, "Yeah, but so is that isn't that true for everything now? Like AI is better. AI is just going to get better at all this stuff. Like AI is going to be able to solve all the useful math problems. What we should be using math for is to train you how to think, to train you how to solve abstract, difficult problems, and to train your creativity. And I just think number theory is the best place to do that. So, today we're doing algebra. Next week we'll be doing foundations. Week after that we'll be doing number theory. And then we're going to go back to algebra, foundations, number theory. Cool. Well, welcome everybody. I can't believe it, but we're actually starting the next chapter now for the first time ever. Wow. I feel great. Like, I feel really great that I was able to solve a problem on the first try. I think that's correct. Where did I use... Oh, the fact that it's one-dimensional representations is implicit in the fact that the vector space is one-dimensional, that the vector space is the complex numbers. Yeah, I use the fact that they're one-dimensional. Yeah. How's it going? I guess it's really kind of implicitly used in the fact that a linear transformation is completely determined on the image of one single element. So any one-dimensional representation is multiplication by an element. And then that element has an inverse. Yeah, I think I got it. Heck yeah. All right. Thanks everyone for watching. Let's keep going. Chapter 4 for the first time ever, dude. I can't believe it. Character theory and the orthogonality relations. I wasn't expecting to get to chapter 4 today. Dude. Dude. This is so cool. This chapter gets to the heart of group representation theory, the character theory of Frobenius and Schur. The heart of group representation theory, the character theory of Frobenius and Schur. I do remember Schur's lemma is a thing. The fundamental idea of character theory is to encode a representation of G by a complex valued function. Okay. We want to encode a representation into the complex, into n by n complex matrices by a complex valued function chi depending on phi from G into complex numbers. Oh wait, G to C. But it doesn't use Blackboard C. I think that's just a typo. So now we're going to describe morphisms. We're getting to some category theory stuff here. Let me confirm that yeah. This is just a typo. The book had a non-Blackboard C for this complex value function chi. That was just a typo. In other words, we replace a function to an n-dimensional space with a function to a one-dimensional space. We replace a function to an n-dim space with a function to a one-dim space. Okay. The characters turn out to form an orthonormal set with respect to the inner product on functions, a fact that we shall use to prove the uniqueness of the decomposition of a representation into irreducibles. Oh, cool. So, like I was saying a moment ago, in the previous, at the end of chapter 3, we have the existence of a factorization into irreducibles, but we don't have uniqueness. So I pointed out a moment ago, okay, we have existence, but not uniqueness. And now this chapter will prove uniqueness of that reduction of a representation. Heck yeah. Okay. So the characters form an orthonormal set with respect to the inner product on functions. A fact and we use this to prove, here I'll write it this way in my notes. Therefore, so this fact that the characters form an orthonormal set with respect to the inner product of functions implies uniqueness of the decomposition complete reducibility into irreducibles. Much of the chapter is dedicated to establishing the sure orthogonality relations which roughly speaking says that the entries of the irreducible unitary representations of a finite group form an orthogonal basis for the space of complex valued functions on G. Okay, that sentence was dense. Let me reread that. All right, so the sure orthogonality relations roughly speaking says that entries of the irreducible unitary reps of a finite group G entries of the irreducible unitary reps of a finite group G form an orthogonal basis for the space of complex valued functions on G. Why not say orthonormal? An orthogonal basis for the space of complex valued functions. Complex valued functions on G. When they say complex valued functions on G, I think that they mean functions from G to complex numbers. Yeah, pretty sure about that. In the next chapter, we use these results to develop Fourier analysis on finite groups, which is central to applications. So next chapter, we can use this to understand Fourier analysis on finite groups. I'm using a lot of non-standard notation. Like I like bar G bar to mean finite groups. Like I think that's okay. It's kind of cheating. Like I'm not completing that sentence. It should be bar G equals N or something. But I don't know. This is my own notes. I'm allowed to do what I want. I guess that sentence does look like I'm saying that we're doing Fourier analysis on a number, on the size of G. That still looks like I'm talking about Fourier analysis on that number. So I could, if I wanted to be annoying, on the set of G such that blah, blah, blah. Dude, on finite G. Okay, 4.1, morphisms of representations. Bro, finally got to this word, this cool looking word, morphisms. Yeah, morphisms are fancy functions. Fancy functions of representations. A principle of modern math is that the maps between math objects should be placed on equal footing with the objects themselves. Yep, category theory. Modern math maps between objects on equal footing as the objects themselves. Dude, I can't believe that Leo and Locke are not here in the chat today. Once I'm getting to some category theory, dude, and they've been like, what's the word, evangelizing, proselytizing category theory to me so much. I think Leo is the first person who used the term that category theory is like a going from object-oriented programming to functional programming, or it's like moving away from object-oriented programming in math. And this is the first time I'm seeing that sentence, like almost word for word, like how he said it the other day. Oh well, maps between objects are on equal footing as the objects themselves. Dude, that's cool. That's just like my experience in software. That's like the same as what I remember. Or not what I remember, what I've experienced. This is so cool. But I remember seeing some of this in the past a little bit, but I never really fully got it. Okay. Keeping this in mind, we turn to the notion of morphism between representations. So now we talk of a morphism. I'm here as a knockoff Leo. Although, warning, I know practically nothing about category theory and lack mathematical maturity, relatively speaking. Well, I'm glad that you're here, at least. I know that we got somebody, somebody is observing me in this really nice moment at the moment. I understand category theory about as much as my cat understands category theory. Like, that's why it's called category theory, because all of us understand it just about as much as cats do. What happened to the views? I remember you were getting 20 average. What's up, geometry? Yeah, I don't know. I mean, we're at 8. That's still very good for me, dude. Yeah, YouTube is, there it comes and goes. Like the algorithm comes and goes. Yesterday was pretty good. Yesterday was 20 plus, like at all times. I feel like the problem is that I am posting like daily. Like I feel like I have a challenge that I'm like just like posting too much almost. But I don't know. I think it's fine. I think we're still on a very good path here. We're on an extremely good path. I'm very confident about it. Oh, you see 15? Let's go. Well, how many likes do we have? Cuz I'm trying to dude, I'm trying not to look at the numbers. When we get to 10, I owe you all push-ups. 10 likes, 10 push-ups. Dude, are you serious? You see 19? We just need one more and I owe you 20 in a row. Oh, you see 18? Okay, we need 2 more likes. If somebody sees 20, let me know. Dude, you all have to tell. You see 20 now? No. Damn it. You all were trying to sneak this on me to get a double. Okay, I owe you all 20 push-ups right now. Oh no. Oh no. Okay. Thank you. Thank you for 20. Oh, dude, I don't do this. I used to do push-ups consistently every day. This is going to be my way to trick myself into doing push-ups. Thank you. Thank you for 20 likes. I think this will help my classical guitar, so okay, numbers 19 and 20 were not as fun as numbers 1 and 2. But we did it. I haven't done 20 push-ups in a row in a very long time, so thank you. Hell yeah, dude. Thank you. Let's get to 30. Let me know when we get to 30. Oh. Okay, so morphisms are fancy functions. Okay, so we're looking at morphisms between reps. Ideas the following. I just don't understand what's wrong with just calling them functions. Why can't they just be functions? Hey, the 20th was your first on your end? Okay. Well, thank you. Thank you for making me do some freaking push-ups. Ugh. Okay, so our idea here is let phi be a rep. We can think of elements of G as scalars. Okay. Okay, I think I see where this is going. So we can map between different representations, like group elements or something, because any two reps are homomorphisms and You can multiply them, and then they represent another representation. Oh, sorry. Yeah, for any group elements, phi g times phi h equals phi gh. So you can think of like the dependency of the image of phi of a group element. Yeah, we can think of that like dependency on a group element somehow here. Okay, so we think of group elements as scalars via g times a vector. Okay, yeah. Okay, that makes sense. So we're like acting on a vector. Yep, by a group element. Sure. This is like how we have been writing this to mean G invariance. It's kind of like multiplying by group elements, but we're not actually multiplying by the group elements, but by the representation of those group elements. Okay? Yep. Okay. A morphism between phi and rho, and rho is a representation into a secondary vector space W, should be a linear transformation okay, so if we have a linear transformation between the vector spaces, then I think we want no, what? So we would have rho T inverse, wait. Rho GW we think of as the group element multiplied by W. And the group element acting on V is phi G V. So then, if we want I think we want something like this. If V maps to an element W, thanks, Sundar. Hey, what do you all think of episode 4? I should ask you all this. Thoughts on episode 4? Loved it. It was alright. Didn't like it. Or haven't seen it yet. Dude, vote in the poll. Let me know. Feedback is a gift. I really, really want to know, what. Because there's a lot of decisions. There's a lot of design decisions I need to make as we're starting the series and as we're continuing it. I want to know what people like, what people don't like. Is it just that people haven't seen it yet? I understand it. Admittedly, you haven't watched it yet. I know I'm posting a lot, so I understand people are behind. I totally get it. All right, somebody loved it. Let's go. 2 votes. One person loved it. One person hasn't seen it yet. 2 people loved it. Thank you. Thank you. Awesome. If anybody has suggestions of what I could do better or what you liked about it, like if there's anything that you liked more about it than episodes 3, 2, 1, I'm all ears. Okay, thank you. Thanks for voting in the poll. Okay, so we have I'm guessing right now. A morphism should be a linear transformation such that such that the transformation of what is GV? GV is an element of the vector space V. So then on the right-hand side, we want an element in the vector space W. So is this what we want? Yeah. Okay. That's what it is. Should be a linear transformation such that we have this for all group elements and every vector. So this is a key idea. Formally, this means T phi GV equals rho GTV for all V, and oh my gosh. Formally, This means that T phi V equals rho. Oh, yeah, because this is, we think of G multiplying, because we're thinking of multiplication by a group element, but we don't actually have multiplication by a group element. We have a linear transformation which represents the group element. Yeah, okay. So I see how this is the distinction. For all vectors, in essence, T phi equals rho T for all group elements. Okay? Now we can write the formal definition, which I think is pretty much the same as what I just wrote. Yo, we got a bunch of people who loved it. Thank you. Thanks for watching the episode already. Yeah. Yo, Sundar. Lol. Yeah. Sundar, geometry says hi. Is BTech worth it in 2 or in 26 or computer science? You mean in 2026? I don't know what BTech is. Is that like software engineering? A bachelor's of technology? I think computer science is not a bad choice. I would study something more foundational, more fundamental than software engineering. Is BTech software engineering, like build Twitter, like how to code, and computer science is more mathy? Like I don't know. I know what computer science is in the U.S. and I think it would be the same. I don't know what a BTech is though. I think computer science is here to stay. I think computer science will continue to be useful to study, but not for the sake of getting into a software job. Like, I don't know. AI is just very good. AI is very good. But if you're interested in more foundational, theoretical, higher level, more abstract computer science concepts, that stuff is here to stay. That stuff, I don't think it's going anywhere. Like the mathier, more foundational concepts. All right. Formal definition. 4.1.1. Let phi and rho I don't know. It's a hard question to answer. There's no clear answer on this geometry. If I were you, like if I were somebody thinking about this, I would really seriously consider studying a traditional engineering role instead. Like if you're trying to get a high paid job, if you care about getting a high paid job and you're not particularly super interested in computer science and becoming like a researcher or working on like more foundational things, and you're interested in a job, I would really consider traditional engineering fields like electrical engineering, chemical engineering, biomedical engineering. I would really think about biomedical engineering, civil engineering. Like, think about, consider, or mechanical engineering. Consider those fields. They're going to be a little more resilient to AI. Like, AI is devouring software. Like, software engineering, AI is really rapidly changing software engineering. Those other fields are going to be a little more resistant, I think. And there's a lot of opportunity for like harder science challenges, like environmental engineering. Like, really think about environmental engineering, bro. Like, if your goal is a high paying job, I'd really think about one of those more traditional engineering fields. In the US, at least, you need to have legal licensure. Like, you have to have a legal certification to be able to legally call yourself an engineer, like an electrical engineer. Any industries that have higher levels of regulation like that, like medical, law, freaking, traditional engineering, all of those are going to require a human in the loop much longer than other industries. Every industry is going to be impacted by AI, and no matter what industry you go into, you're going to be using AI. But I think we're much further away from fully automating chemical engineering or biomedical engineering. I think we're so far away from fully automating that than something like, software engineering. There's just not as much data out there. There's not a GitHub for those fields as much, and there's more regulations. I think that's a really big reason. And then on top of that, like, AI will come for those fields too. But by then, if AI has made, though, like, medicine, and like, I'd really think about medicine too. Really consider medicine. Medicine and traditional engineering fields are going to be much more resilient. And when AI comes for those jobs too, then everybody is messed up, man. Like, everything has changed. The entire world needs to find something new. Like, every single industry is wrecked by that point. That's my opinion. Like, by the time that AI does come for those industries, everything is wrecked. But software is ahead of the curve. Now, if you're interested in math and like math research, AI is just as good at math as it is at building Twitter, at like software, just building an app. Like, there's an app for that. AI is just as particularly good for math as it is at building apps. And like, if you want to contribute to this, questionably valuable, like, no, we don't really know. I don't know. Just arguably, it's like kind of pointless. But AI is just this totally alien life form that is making math research super, super, supercharged. I don't know about the math thing. You don't agree? Man, I mean, the Jacobian conjecture just a couple days ago, AI is just supercharging, counterexamples, formalizing thousands of lines of lean code. It's not just AI, but the advent of AI and lean at the same time, like both of those together are I think from what I can tell, just a new era of math, like a new era of math research right now. Um, like, I'm not saying that it's going to fully automate math research at all. I definitely don't think so. But it's transforming. I think AI is transforming math research very, very similarly to how it's transforming software engineering. Like, I still think it's a lot of hype. I don't know, dude. I don't know if I don't think it's a lot of hype. I think that the hype is well founded. Did you read Kevin Buzzard's blog post about this a couple days ago? I think it's definitely worth a read. I mean, I've been following Kevin Buzzard since 2020 when I started paying attention to lean and dude, I mean, it's so I don't know. Here. This is I really enjoyed this Kevin Buzzard on on AI counterexamples, the Jacobian conjecture, just 2 days ago or something. It'll be a new tool, just like computers were a new tool, currently an extremely unethical one. That's a deep question. Currently extremely unethical. I don't. Yeah. I mean, I could make that argument. I could definitely make that argument. I think that somebody could make the counter argument too. I do think right now, if you are a knowledge worker and you're not learning how to use AI, you are making a mistake. I mean, unfortunately, it is objectively unethical. Yeah. I want to engage in this discussion because it sounds fruitful. It sounds really interesting. This sounds like a fun conversation, but dude, Locke, you just tuned in. Bro, I'm glad that you're here for this. Look at this. Dude, we are getting away from object-oriented programming and we are getting into functional programming, dude. Like, the maps are just as important as the objects themselves. So I'm glad you're here for this. We're learning about fancy functions today. Yay, morphisms. I know, right? I know. Yeah. The problem with accelerating math research is that we lose the plot of the value math research has. Yeah, but the thing is that I don't think that we're automating math research. I think we are, like, I do think way, way, way more than the idea that, like, oh, AI is a tool that's accelerating software development and it's a tool, but there's going to be somebody at the helm. It still requires a human in the loop guiding the AI. Way more than, I mean, that might be true for software engineering, for building apps. Maybe that's true, but way more than that, I think AI is now this tool that aids mathematicians, and a mathematician should be learning how to use it effectively in order, like, AI is going to be like spewing out some incomprehensible proof, but it says like, hey, here's the lean code, here's a million lines of lean code that proves this question that you were asking. And then it takes a human mathematician to understand and like refactor and simplify that proof, like ask the right questions in the first place, and then most importantly, know what the next questions should be. Like, I think way, way, way more than software engineering, it requires a human in the loop to understand the results and to know what the next questions should be. That's my understanding. 5 more likes. Okay. The Primogen had a video against the very take you just said, that you're missing out if you don't use AI. No, I mean, well, so the Prime has been saying this for a while. He's learning to use AI. Like, no, dude, Prime. He's been saying forever that, like, oh, it's not true if you're waiting to see until the dust settles. And he did wait to see until the dust settles for a while, but he uses AI all the time. He is currently using it all the time. I know that he turns it off every now and then, and he still writes code by hand, but it has changed his daily workflow for AI. Like, you should... I'm not saying that a software engineer should fully lean into the vibes and just vibe code, but you should be learning how to use it in a smart way. And a smart way is not 100% AI. That's a dumb way to use AI. But you should be learning how to fit it into your workflow. It is too late to say that you're just going to wait to see whether or not it's useful. It is clearly useful, and it is a new expectation in performance reviews at every company now. That's my understanding. Keeping in touch with a lot of my colleagues, former colleagues in jobs. Like, if you're not using it, then you are being seen as unproductive compared to somebody else. Which Primogen video? I need to see this. Because, I mean, he's just very strong about these ideas. Okay, 19 hours ago. Okay, that's pretty recent. You won't fall behind. He's been saying this for a long time. I feel that this is not going to be different than every other time I've heard him say this. I don't know. Man, I don't know. I think you need to be paying attention. I do think that, like, I don't think that you're going to fall behind in the sense that you can't catch up. I do think that you can catch up, but it's clearly here to stay. It's clearly transforming software. It's clearly transforming math research. I think it's going to be a while until somebody's going to regret not using AI in math research, but like Kevin Buzzard's article proves something to the counter argument that, like, now universities are paying for expensive licenses for their grad students. Like, these tools are tremendously powerful, and I do think that you want to be trying to learn how to use them. And you can also make the argument that they are unethical and that we shouldn't have them the way that they're built, but I don't know. We're reaching into some thornier, deeper questions about ethics that I don't feel like getting into right now. Because I study philosophy. I took 3 ethics courses, so I would love to navel gaze on this, but I'm not going to. Okay, morphisms. Primogen video, blue perks, I can send links. Yeah, you can. Yeah, dude. Also less serious, but sometimes when people hype some new model, I try to ask it math questions how I would in research, and it for now has been horrible to say the least. I don't know, dude. That's not the take that I'm hearing from mathematicians I know. I'd also listen to Cal Newport, who's a mathematician at Georgetown. He's a theoretical computer scientist, and he's like one of my favorite authors, dude. That book is usually in the bookshelf back there. It's called So Good They Can't Ignore You. He's got a podcast on like smart productivity stuff. He has this take. Like, I'm heavily influenced by his take on this, that yes, AI is transforming math research. No, don't worry. It's not going to take your jobs. It's not going to completely radically eliminate math as a human endeavor, but it is an amazingly valuable tool, and he wishes that he had it when he was a PhD student. It's already transforming his daily workflow. Like, I don't know, dude. Like, people like Cal Newport, Kevin Buzzard, like a lot, like, I mean, I don't know, on a smaller sense, like K theory. K uses AI all the time in his streams to like ask specific questions. I I don't know. I don't know. I think that there are smart ways to use it. I wouldn't say it's horrible to say the least. I'm already using it, man. Like to try to judge my proof or check some statement or something, or just like quickly as like a reference, instead of like opening my Dummetin foot or something. Like it's already very useful, dude. Um, so relatable. For example, writing even very, very simple programs in cast systems, which are not as huge as Sage, is not possible. And yeah, there are things that it just doesn't have as much data for. It makes me question how useful it'll be for more specialized tools where there are not 10 trillion public GitHubs to steal the code from. That's what I'm saying as well. Like, this is why it's particularly good at frickin', just mimicking apps, building apps. There's like 10 trillion public GitHubs. Like we shot ourselves in the foot by thinking code should be open source in this like beautiful, utopian world of just sharing everything for free. We shot ourselves in the foot by giving away everything for free, and now the tech bros, put us out of jobs. The tech bros took advantage of our beautiful utilitarian, or our beautiful utopian mindset of free open source software. But the thing is that AI now can write lean. Like my original take here, my original claim was not that AI on its own is going to transform math research. It's AI and lean. Lean, like even without AI, even if ChatGPT didn't, come out a few years ago, lean is just as big of a revolution, I think, in math research. I know that it's not like the first formal system. Like we have Rock and whatever, HOL, Isabel, whatever, all those like older ones, but like lean is the first one that's just so much more ergonomic to use as a math researcher. It's just the ergonomics of lean are just so much better that I think it's the first system where we can start to expect formalization of math research papers. Even if we were writing all that by hand, it is possible to write that by hand. Like, you can do it. It's not that hard. It's not that different from beautiful white paper math. And I think both are going to be here to stay forever. Like, I just think we're going to continue to have, I don't know about forever, but like, I think for the foreseeable future, we're going to have white paper math, beautifully typeset in LaTeX, and just beautiful, it's like a work of art. And then we have the down and dirty assembly language, formally verified, type theoretic, lean proofs of those results. And so you have the beautiful art argument, and then you have the like concrete, here it is, here's the, like it compiles, this mathematical statement is true and we're confident. My chat is not refreshing, but I see it is refreshing in the other thing. The advantage is that Lean has a great PR team, right? Yeah, Lean has just a terrific marketing team on it. Yeah. and private. There's definitely an oh yeah, true. Yeah, I mean it doesn't just have to be the public repos. It can also be all the private repos because Microsoft has a large stake in the in the frickin' machine. Um, there's definitely an ethical way to do AI, but current companies just do not follow any of the possible ways. Yeah, we didn't shoot ourselves. Companies hungry for money abuse the open nature of free open source. Well, but I don't know. Like if you put stuff out trusting other humans to be good, and then and you pretend that there's not, selfish tech bros out there, did you shoot yourself in the foot? That's like, like if you expect that somebody else is not going to take advantage of you and you do something and then they take advantage of you, like, did you shoot yourself in the foot? I don't know, dude. I don't know. Which sucks. It just sucks. Like, it's not, I don't know, there's like a precise definition of terms here that would be fun to engage in, but I don't want to go down that rabbit hole. Although TBF, companies, corporations in general have been extremely evil for a long time. That's what I mean, right? Like, we think, oh, let's just put out like all of this. I mean, nobody could see. I don't think like it's an understandable error to make. like software engineers didn't see this coming, that somebody was going to be able to scrape all of the public GitHub repositories and then train, an amazing, supercharged next generation machine learning model. We just didn't see that coming, and that's maybe understandable. But maybe there's just something in the idea that, like, maybe we shouldn't have just been giving everything away for free. Maybe we shouldn't give away everything for free. Maybe that's a beautiful utopian ideal. But maybe it's just as a system not a good idea. And I'm saying that with a lot of self-awareness about what's happening right now. I'm giving away the stream for free. Everybody's giving away content for free, expecting, that you're going to get some kind of return in another way in the future. I don't know. I think that this would be an interesting direction to take this rant into, but I'm trying not to. It's just, I don't know. It's a beautiful utopian idea, but then, there's gonna be evil people out there that just take advantage of that. Lean has a great PR team. Yeah, people keep going about AI and Lean. This is at least partially true, but I still have some gripes with how people imagine this to be, but this would get a bit too philosophical for here. I mean, I studied philosophy. I have a minor in philosophy, so I would enjoy it, but I don't want to do that. I'm just saying, DZ John He, read this blog article that I just shared from Kevin Buzzard, and if you're not already paying attention to him, I'd start following Kevin, because I think he's a smart dude. He's got really good points. It might be overblown. I don't think it's going to completely radically transform everything about math research, but it's going to change. Like, it is going to have a major impact, and it is a tool that is very useful to learn, I think. It's like saying certain technological advancements should be inhibited because the military can make use of it. Yeah, right. Like, it's an interesting ethical question. Like, that's an interesting ethical debate and dilemma. You know, like, uh, I wish I should just start showing up to philosophy, to like ethics lectures today and like seminars, because dude, I think that they must be having a field day. Like philosophers today, like ethicists must be just like oh my god, like our field is now more relevant than ever. Like this very theoretical field is now more practical than ever. Um, like I would love to watch those discussions. Luna is asleep and she is like quivering. She's like dreaming right now or something. Hey, what's up? How's it going? Divya, right? Int main void nil. That sounds like that's a programming. I've never actually read your name. Java? Is that a Java reference there? Yeah, what programming languages has int main void nil? Yeah, I was like, well, Java doesn't have nil. Yeah, it's similar. That's true. Philosophers, your dad is a professor of ethics, are having a field day. I bet that they are. Dude, I haven't even thought of this. I'm gonna just start showing up. I just want to start showing up and auditing and just observing because, bro, that would be so cool to just like see these discussions between really smart philosophers talking about the ethics of AI and the impact of AI. Like, oh, dude, I want to be in that room. Um, yeah, it's Divium. That's right. Java is similar, but it's just so gnarly and disgusting. Yeah. Oh, Johnny. Okay, what's up, Johnny? Yeah, thanks for correcting me there. All right. Well, anyways, this is much more. I mean, this conversation is interesting, but also the math today is very interesting. It's the first time that I'm getting to chapter 4 on category theory and morphisms, and dude, this is like a big day for me. Like I'm seeing category theory truly in context for one of the first times. Here we go. So we're moving away from object-oriented programming into functional programming, like this eureka moment. The functions are much nicer to work with than objects. Let's keep going. So let phi be that, and rho. So does this book reserve psi to be an equivalent representation, I guess? Because these are not equivalent. They're just two different representations. Okay, so these are reps. A morphism from phi to rho. Man, this is mathematicians like gatekeeping. Phi and rho both look similar. Rho looks like you should just call it p. Like, this is math gatekeeping right now. A morphism from phi to rho is by definition a linear map T from V to W such that T phi G equals rho G T for all group elements. In other words, the diagram commutes. Yep. Fiji. So we have a map from V to W W to W is rho, and V to W, again, is this map T. This diagram commutes for all group elements. You can draw a little backwards curly arrow to say that this diagram commutes. Okay, sick. Dude, this is really cool. This is super cool. Okay, let's see. Give me 1 second. Small write-up that guided... Yeah. So I've seen a little bit of category theory thanks to Locke. And I learned a little bit of category theory in context. Okay. Let's turn the representations into a category. One of the first times sad direct product noises. Yeah. I do. I'll give you credit. I've seen category theory. I learned a little when I audited this class, Big Boy Lang algebra. I tried to learn algebra from Big Boy Lang, and I learned a little bit of category theory there. I did that exercise from you, Locke, and I really appreciated that. Rho has a little tail. Does it? No, it doesn't. Rho does not have a tail. Not in this font. This font does not have a tail. It's not quite as vertical straight as I drew it here, but my handwriting's not perfect. Rho has just a slant, and it looks like this. So it's like a little more slanted, but at the same angle as phi. They look damn similar. They look damn similar. Like, they look the same. It's just that phi has like a little... It's more like phi has a tail, whereas rho is missing the tail. Like, maybe you meant to say that backwards. Like, phi has... It's a little more... Maybe if I start drawing it a bit higher. Curly phi. There is the weird phi. There's a weird looking phi, but most people write the curly phi, right? We love commuting diagrams. Yeah, a representation is a functor from the group as a one object category to the category of C. See, that's a refactoring that I don't understand yet. That's a re-architecture. I understand this architecture. I understand MVC. I understand model view controller, bro. I can understand model view model. But now you're trying to go all the way to like Redux or something, and like, bro, my mind is blowing up. Like, you're trying to go to the hexagonal architecture or something. I'm not ready yet, but we'll get there. A representation is a functor from the group as a one-object category to the category of C vector spaces, and a morphism is a natural transformation between these functors. That's sick. I look forward to writing that. Okay, well, I write it with a tail. Okay, so you're saying that you do this? You add a tail to your rows? That makes sense. Like this? I love it. Yeah, phi's left part curves upward, so I fixed that, didn't I? Yeah, var phi is much better than phi. Yeah, nobody writes phi. I wish that we could swap those in LaTeX, right? Because var phi, like, everybody writes curly phi. Rho is just p but more round. Yeah, rho is like a weird, just slightly off looking P. It looks like P, but it's just a little different. It's like a little more slanted. I think that's a better looking row. It's just kind of a weird P. Okay, tips defaults to phi, so it gets automatic plus points. Fair. I realize, I don't know if you can do this in LaTeX, in like compiled LaTeX, but you can in KTeX at least, and or most specifically, you can in the app ZenNotes, which is what I'm using. It's like a Vim-based alternative to Obsidian, and it has KTeX support. You can just use the Unicode symbols themselves. So I'm just using the Unicode fucking symbols. Like, I want my code to use Unicode. Some people might hate that. I love it. Dude, you can just use Unicode. And then your code looks like how it renders. I don't know. Some people think that that's like really sacrilegious or something, but no. It's actually very nice. You get used to it, especially in Lean. In Lean, you get used to it. You can make a macro. I just use the Unicode symbols. If you remember, I asked the day before if I still have the time to study maths after failing. I spent the last day grinding calc, and you're getting a hang of it. Nice. Unicode, when you have math mode available, is so cursed. Nah, dude. Unicode is great. Get used to it. Just get used to it. Get used to it. Like, you add text expanders in your system keyboard. You just add text expanders. I use things like all of my text expanders start with the semicolon. And so when I type, semicolon phi, technically speaking, I don't do that. I do semicolon u phi. Yeah. Semicolon u phi, no space, and it just automatically expands. Let's see, what else do I have? E, cool. I don't know, that's the first thing that came to mind. U, pi. Dude, just frickin' do that. And then you can, like E fire. What? I don't have fire? I definitely use E guitar all the time. Well, I don't write any. So this is, yeah, okay. That's an understandable question. Like, how would you do that if, like, is there ever a chance that this might become a problem when you're coding? The simple solution for that is don't write any fucking languages that use semicolons. I'm gonna argue that to the grave. If you're writing a programming language that uses semicolons in 2026, you should rethink your life decisions. Very much. Rethink your life decisions if your language requires semicolons. That is the weirdest take ever? No. Think about it. It's true. It's true, dude. Does Rust doesn't require semicolons, right? I mean, I don't know enough about Rust. Like, if you're writing C++, why aren't you writing Rust? If you really are that masochistic that you want to write something like C++ or Rust, why aren't you writing Rust? Does Rust require semicolons? Oh, it does. Oh. Okay. Well, that's weird. Yes, Rust requires semicolons to terminate statements. However, you omit them on the final line of code blocks to return values. Okay. So wait, if... Oh, wow, all right. So in the last line of a function, they're optional? Oh, okay. Great. Now I have an argument for why you should use Swift instead of Rust. There we go. Heck yeah. Now I have a better argument. Now I have a new argument for why you should write Swift instead of Rust. Huh. What compiled language doesn't use semicolons? Swift. Dude, Swift. It lets you omit the semicolon for the last line as an implicit return. Rust is expression-oriented, something more langs need, not just function any code block. Yeah, Swift does that. Does Elixir require semicolons? Yeah, Elixir does not. In Elixir, line breaks act as a default delimiter to separate statements, and you can use them if you're writing multiple statements in one line. Dude, heck yeah, I have a new argument why you shouldn't use Rust. Does Zig require semicolons? Okay, it does. See, this is... okay. Does Go require semicolons? It does? Okay, I'm very Swift-pilled. Like, I'm very Swift-pilled. And somehow a couple of other languages I use don't require them. Ruby doesn't. Love Ruby. Does, what's another popular one? I don't use TypeScript, but does TypeScript require semicolons? I don't think so. No, it doesn't. That's what I thought. I didn't think it does. Does Swift do semicolon injection like Go? Please tell me it doesn't. I don't know what that means. Go semicolon situation is extremely cursed. TypeScript is optional, but I always put semicolons in TypeScript anyways. Just get you like, oh, it's so much nicer not to have the stupid semicolons. Like Swift, I've never worked in a single Swift code base where people wanted semicolons, even if they're optional. Nobody writes semicolons. No sane code base requires semicolons in a Swift code base. I've never seen it. It's lovely. It's just so pretty. I don't know what you mean by semicolon injection. It's just every line is its own expression, and the new line delimiter is the end of an expression. No, I don't think Swift's handling of semicolons is quite like that. It's a little different. It's a little more strictly typed than... It's not just like a simple... At the end of every line, we put the semicolon. Like, I've never heard of that kind of compile error. It's not that naive. It's more complex than that. Does Haskell require? Haskell doesn't, right? I don't think so. It doesn't. Yeah. Okay. So we've got meaningful white space. No language should ever do what Go does. Interesting. Okay. Anyways, we went from typography of row into semicolons and a lot of other weird tangents. Let's keep going. I love that we're getting to chapter 4 now. The set of all morphisms. Neat. So I'm thinking of morphisms as higher order functions. So they're functions that return functions. It's a function that maps from a function to another function. Higher order functions. The set of all morphisms what's wrong with that thought? What's wrong? I mean, I guess it's that the morphism is the linear map. This linear transformation is the implementation of the morphism, but we are thinking of it as a map from two representations, right? I guess. Okay, so if it were me and I was making up stuff, a morphism, we're going to give it like a fancy M or something. A morphism is a higher order function which takes a function from a group into a vector space V and returns another function right? So if I give the morphism phi, it returns another morphism rho. By a linear map, it's implemented by this linear map from V to W. Now, does a morphism require... Can I define other morphisms that are not built from linear transformations? Can I define a morphism, fancy M, from any objects to is a morphism just a higher order function that takes a function and returns another function? Or is the fact that it's a morphism, does it depend on something like the fact that the domain matches? Does the domain need to match to call something like this a morphism? Or does it need to be as strict as some kind of boxing with a supplementary map, another map that maps between the boxes? I feel like here we're getting to something where we've got this box around an object and we need a supplementary function that maps between the boxed values. I think that this is where we're coming to a more generic setting of a morphism. Or I might be defining a functor right now. Is that what a functor is? It's like a fancy function. Is the functor... I think the functor is going to be the map between C to D. That like secondary supplementary function. I think that this thing is the functor, and a morphism depends on a functor. And I'm guessing that the functor doesn't have to be unique. If you have one linear transformation between the two vector spaces, that doesn't have to be the only one that's possible, I think. So, with all this, I have a morphism from phi, which then returns another representation rho. And I think all of these need to be subscripted with G, but it needs to be true for every group element, so I can just write this, I think. So I could say maybe something like this is what I'm predicting right now. And now I'm going to read chat, and you all are going to help me. How close am I? How close am I? I might be totally off. I mean, you could think of it that way, but the underlying datum of a morphism is just a normal linear map between two normal vector spaces. Okay. The underlying datum of a morphism. So the morphism is the linear transformation of the vector spaces. Haskell has do notation. Yeah, I was thinking of that. Yeah. In this case, it's fine. This is the most programming-brained view on rep morphisms I've ever seen. Not entirely right. A morphism takes two reps as an argument. Okay. So I thought that the morphism... Aha. Okay, wait. Are you saying that a morphism takes two representations I'm gonna fucking do this, dude. I'm gonna make this type alias, and you all know what I mean by it. So it takes two representations. Oh wait, the second one was W. And then if it takes two representations as its arguments, then it returns an element of, oh wait, not GL, but a linear transformation from V to W. So if you're saying that it takes two representations as arguments, then it needs to return something, which then I guess would be it would return the transformation between their vector spaces. Maybe? It returns a set of linear maps as return value. Okay, it returns a set of them, not a specific one. Okay. The morphism doesn't take phi itself, it takes the vectors of phi and returns other vectors. This is a bit off. Okay, I'm trying to figure this out. I'm trying to predict before I read the book. You know, I'm just trying to like actively pause while I'm reading, try my best to predict what's next, have an idea of maybe something that I would implement if it were code. What's up, Heidi, by the way? And then it looks like I'm building something named different. Like maybe my naming is off, but maybe I'm building something that is still useful. Maybe it's hum. It doesn't make sense to evaluate a morphism in this case. Okay, I thought that the morphism... So what have we written so far? A morphism from phi to rho. So, like, I still feel like it makes sense to say of a morphism... Okay, wait. Is the linear map... Okay. So I'm a little closer, I think. Well, I don't know. I feel like what I was thinking makes sense still. I'm thinking like definition of a morphism from the definition of this morphism, we implement it by the implementation of this morphism is, as it said, by definition, the linear map between V to W. Okay. So what Lockheed just said is closer to what I ended up writing. Oh, maybe I didn't write it, but I ended. Oh yeah. This is. Yeah, I guess that this is pretty similar to what Locke said earlier. I'm still catching up in chat, but I think this is pretty close. Like you just have it curried, but still a two functions as arguments, and then returning a set, but a set of, you're saying it's a set of linear transformations from V to W. That's kind of crazy. Really? JC going wildly off with this one. I'm trying. He's got the spirit. I'm trying. That's a whole point. That's what can be different about this stream. Do not trust any of the math I'm writing on screen, like especially when it is new math to me. I don't have a clue. Like I'm trying. I'm trying to think out loud and share my thought process as I've paused in this book and like try to predict what's next. And you all are helping me. Maybe JC wanted to describe the hum functor, but went a bit off. Haskell category theory. Is Bro actually introducing programming notation in here? We should. Trying to explain things in the mini YouTube chat has got to be one of life's supreme challenges. Yeah, without like LaTeX support and things like that. It returns a set of linear maps between them. I do think he's nice. He's trying to predict what the notion will be. It'll make you think more critically about the definitions when you read them. I think that this is good, like an example of good deliberate practice reading math. Like you should pause, like after a sentence, pause and try to think about what you just read and try to predict what the next sentence is going to be. Like a simpler version of this is like you read the theorem and then you try to prove it yourself before you read the proof. But then as you're introducing new definitions, try to like just think, okay, like, oh, I've heard of these words. I've heard of a functor. Maybe functor is going to be XYZ. Let me try to invent it. Let me try to predict what's next. And then I'm going to read and I'm going to be like, oh, I was wildly off, but maybe I made something else. Oh, turns out that this was hum or something like that. Because in general, you don't have a canonical linear map you can put as a return value, so you return the set of all of them. Okay, sick. Yeah, that's why I was thinking that a single morphism is implemented by one linear map, but a morphism returns all possible linear maps. Okay, nice. You might be right. I might have understood what JC was trying to get at. It looked like the closest notion to me. Fair, but explaining two distinct but related things at the same time got to be so confusing. Sorry, off topic. What do you wondering? Do you call it zero or the letter O? What do you mean? Here, it's not written here. I say zero or not. A lot of people say not, which is like, I think British English. People say not for like NAUGHT to mean zero. I say zero, or like if it's something like X naught or A0, A subscript 0, it's very conventional to call this A naught, because it's being naughty. Isn't that, or null, Aleph null, isn't that, I'm not making this up. Oh, okay. Yeah, all for naught, describe an effort that produced zero results or ended in complete failure. Additionally, it can refer to the arithmetical symbol zero. Yeah, this is very conventional to call something empty like this naughty. This is a naught. But in other places, somewhere like 0 plus x equals x, I use definitely 0 in that context. Aleph null. Yeah, ugh. Don't get me started on null. Don't get me started on that one. Okay, so I was wildly off, but I'm trying to make up some stuff and understand this definition a bit more. So we still have a morphism from phi to rho, and by definition, it is a linear map. So what's confusing me that doesn't match what you've told me in the chat is that this definition right now is referring to a single morphism, and it is a linear map. Whereas you're saying that a morphism between these representations is a set of all linear maps between them. And this morphism between representations also has this requirement. So in programming, in Swift, or other modern languages, you can say that this is like a protocol, I think. This is a protocol that it's a requirement that this diagram commutes. So I wouldn't have guessed your definition that it returns a set. Okay, yeah, your thing is technically the set of morphisms packaged as a function. And you forgot the commuting requirement. Yeah, me too. I mean, I was forgetting to add that requirement. But yeah, you were talking about something more like the set of morphisms or something. Maybe we call it MOR or something from representations of into V and representations into W or something. This is the set of all morphisms of specific reps. Which return a single linear transformation from V to W, right? Then therefore I don't know, man. I'm just guessing. Let's keep going. This set is usually called hom. I think that's literally the next sentence, actually, in this book. So let's keep going. The set of all morphisms from... Yeah. The set of all morphisms from phi to rho is denoted hom G phi rho. Yeah, okay, so a single morphism. I see what you're saying. Yeah. So this thing, in my notation that I was inventing, this would be hom. And the book is saying that this is hom of two specific representations. I was thinking hom of the set of all representations. But, okay. Notice that hom G... Okay. Notice that hom of phi rho is a subset of all of hom of VW. Yeah, okay, that makes sense because The first one is this is the first one is this set. The set of all linear transformations such that phi... Shit, how does this go again? Right? Yeah, T phi equals... T after phi is the same as phi as rho after T. T phi equals rho T. T phi equals rho T. Yep. And since this is a restriction of linear, this is like a protocol or like a behavior of linear transformations, then this is a subset of all linear transformations, which is denoted HOM. HOM is just a type alias for that set of all linear transformations from V to W. So it makes sense that this first one is a subset of the second. Okay. The word morphism should remind you of homomorphism between groups and vector spaces. Yeah. It's an individual map compatible with the extra structure. Yes, that's why I was thinking. I think that's where I'm coming from. That it's like it should be a single map, right? It's an individual. So, dude, was I right and Locke was wrong? Like I know that Locke was accurate in a lot of things, but like overall, was I right and Locke was wrong? Overall, was it closer to I was right and Locke was wrong, or Locke was right and I was wrong? Locke was describing something else. So I think exactly. I think I was right and Locke was wrong. Hell yeah, dude. Hell yeah. All right, let's keep going. I mean, I was also wrong. Both of us were speaking of slightly different things, of course. I misinterpreted what you were trying to do. Got it. Heck yeah, dude. I'm not completely wildly off. That helps me know that I was like at least on the right train of thought generally. Okay, so note that hum of phi rho is a subset of hum VW. Yep. Remark. If yep. Yeah. I was thinking this earlier. I was thinking this commutative diagram is almost identical to similarity, but we didn't have the requirement that T was invertible. if t is invertible, then it's the same as saying that they are equivalent. But right now, this definition does not require an isomorphism. It just requires a linear map, not an isomorphism. So, remark, if t is invertible, then phi is similar to rho, and t is an equivalence. Yep. That makes sense. Maybe the functor stuff you're talking about was trying to relate to this. I think I was way off on the functor stuff, yeah. If hom is a functor, contravariant in the first argument and covariant in the other, I don't know what that is. No. If you have a morphism of reps phi to psi, then you get a function hom psi rho and a function. Whew. Lecture series for real analysis. I don't have a good recommendation. Yeah, I can't. I don't know any. I took classes at university. I don't know. There's probably some pretty good ones out there. Probably MIT OpenCourseWare. Like, that's the first place I would check. Like, I promise that they have lectures on real analysis. Yeah, I've always seen isomorphism before morphism. I've always seen that. I've gotten comfortable thinking of isomorphisms, and I've known that the word morphism exists, and that someday we'll talk about morphisms, but that isomorphism is like is something that you learn first. Yeah. Okay. Okay, so we've got that remark. And now we have another remark. Observe that. Okay. If the transformation is of a vector space into itself, W equals V, then we're talking about hom V into itself, which is the same as like Axler uses this notation of LV. Hom V, they don't need to be invertible, right? But isn't there a... No, I think we just write it hom V. I think we just write that. Okay, so what would be next then? Observe that if we have a linear transform like that, then both of our reps are rho t equals t phi. I think t phi equals rho t. It's more conventional to write, but this time I thought of the square in my head and was able to write this down. And if t is I don't know what's next. I don't know. Okay, so well, okay, yeah. So observe that any map of the vector space into itself belongs to Hom. Okay, so Hom of phi phi. Yeah, okay. Yeah, certainly, because then, of course, t phi equals phi t, right? Is that always okay? So, I mean, this set requires phi t equal t phi. Um, I think I follow that. Okay, if and only if t phi equals phi t. Yeah, so if and only if. I was just thinking, like, that's not always going to be the case, but yeah, okay. If and only if. Uh huh. If and only if. T phi equals phi t for all group elements. I.e., in essence, t commutes with or centralizes. I remember this idea in algebra. Centralizes phi of g. In particular, the identity map is always an element of hum phi phi. Okay, yeah, that makes sense. What is, I mean, what phi g? I think that this is the set of all phi. I think that this is true, and then t commutes with this means that if t commutes with the t commutes with then I'm just going to temporarily switch to, for every transformation in Fiji, TF equals FT. But really, yeah, for every group element, yeah, okay, so that's what commuting with a set means. For every element in that set, this other function commutes with every element in the set. Okay, I think I'm used to that language now. In particular, it makes sense that the identity map, in particular, the identity map is always an element of Hom phi phi. As is typical for homomorphisms in algebra, the kernel and the image of a morphism of representations are subrepresentations. Sick. Hey, Jack Mac, bro, thank you. Jack Mac, are you here in the chat right now, or Jack Mac, were you subscribing to watch the recent live stream? Dude, if you're here, let me know. I would love to work a problem for you if there's something that you'd like to see. Or in any case, I'm definitely... Yeah, you're here. Heck yeah, dude. Thank you for joining as a hobbyist. I appreciate it, man. Do you wanna see a problem from basic math, or do you want to see me study some more representation theory right now? I subbed to watch some of your other live stream VODs. Hell yeah, dude. And not only did you sub to be a Luna member and just see the other live stream VODs, but you also want to see the weekend basic math streams, right? Bro, thank you. It's nice to meet you. The category of representations is an abelian category. I'll get there. I don't even know. Yeah, man, thank you. Nice to meet you. What's your story, Jack? I owe you. Here we go. You're going to get your name in the thank you note. You are a hobbyist and everything, bro. I'll watch you work through some basic math, but I have class in 15 minutes. Okay, yeah. Let's see if I can do one or two real quick for you, dude. Jack Mac 8715, thank you so much for supporting my journey, dude. Yeah, let me quickly hit an exercise. Have you seen my episode 4 on multiplication yet? If not, well, in any case, I think that you'll be able to follow these problems. Dude, thank you. Let's see. Okay, I've already done number 1 with like a bunch of expressions, and I've personally already done number 2. Let me work number 3, which says obtain... not yet. You're planning on watching after class. Okay, so if you haven't seen some of the previous ones, I'll work 1.3.1a. It says express in the form 2 to the m, 3 to the n, a to the r, b to the s, where m, n, r, and s are positive integers. It says out loud, or like it writes out the phrase positive integers, but okay, so part A, we've got 8a squared b cubed, 27a to the fourth, and 2 to the fifth ab. Okay, so this is our first multiplication exercise. I think it's pretty cool. All right, so we can regroup parentheses, and we can rearrange multiplications by commutativity. B cubed times b. So in a proof, I would justify this by associativity and commutativity. So let's remind ourselves associativity in multiplication is this property that you can regroup parentheses. 1 times 2 times 3 or 12 times 23 times 34 equals, any order of multiplying them in the same order. And then in the real numbers, in the numbers that we're working with, multiplication is commutative. So the first part was associativity, and then the second part is commutativity. And I use both of those repeatedly to rewrite all of the numbers on the left, and then all the variables a, and then all the variables b multiplied. Now, 8, I can write as 2 cubed. 27, well, let's do 2 cubed, and then rearrange and do a commutativity swap. 2 to the 7th, you can convince yourself that that is 9 times 3, and 9 is 3 times 3. So 27 is 3 cubed. For the sake of my proof, I'm going to keep these two portions as is. So this was by definition of a to the n. 8 by definition is 2 cubed, and technically I did also do a commutativity swap as well to swap the order of those two. So we got the definition of a power to rewrite 8 as 2 times 2 times 2. And now we can get 2 to the 8th times, at this point, well, yeah, let's keep the parentheses. 2 to the 8th times 3 cubed times a to the 6th times b to the 4th. And the property to justify this line, this step, is that a to the m times a to the n equals a to the m plus n. This is a property that we've proved in the section. And now I can drop all the parentheses because multiplication is associative. So we don't need parentheses in a series of multiplications. Thus, now this is in the form that we wanted. M N R, our powers M, N, R, and S are 8, 3, 6, and 4. This is in the form that the question asked for with these powers. Cool. So that's exercise 1A. And then if you still have time, I'll do another one really. That's a really solid breakdown. Thank you. Heck yeah, man. Heck yeah. Yeah, just like this is the same kind of problems that you've seen in school, but now we're being careful and saying exactly what, math property we're using every line, like every step. We're justifying why we can rearrange or regroup parentheses. Like every step is justified by a mathematical fact that we've proven and seen before in the book. So everywhere else I've been writing a sock to say associativity, so let's keep it like that too here. The book even gives these labels like, I don't know, this might be N7 or something. You could say N7, or you can write out the entire property. Don't know if I truly have enough time. I only have 8 minutes. All right, well, let me show you number 2. Or, yeah. Instead of number 2, you're going to use this fact in order to work number 2. In the book, we show this property. I like to put like a little question mark. Our goal is to prove that this is the same as this. And you'll see in my video, I talk about how Lang calls this poetry. And it really is poetry. It's beautiful. It's a beautiful math fact. So let's prove it. Proof. The distributive property of multiplication shows that I'm going to switch to X, Y, and Z. This is the distributive property, technically on the right, but that's for some reason how I like to think of this one. Thus, using X equal A, Y equal B, and Z is this number. So remember that A plus B itself is a number. We have by definition of a power, this is the number A plus B times itself. Now, this is a step that's a little confusing if you haven't seen this already. And so I just really want to call this out. This is X plus B times Z. Z think of z as this entire number. This is some number. And now we have xz and yz. You wouldn't write in a proof the yellow parts, but you could, like, it just helps to explain this step, I think, for those who haven't seen this a lot. And then again, by distributivity, you multiply a times a times b times a, and b times b. Now, I'm doing two steps at once. One is the definition of a square power, of a second power, and then also I used commutativity. So here it's important to notice that we used commutativity, and now we can add those two AB terms together, and therefore we are done. We got to draw the cute little square. All right, I hope I finished that in 8 minutes. I think I did. So this proves, that proves this identity. And finally, last thing I want to say is, like, don't think of this as the a plus b squared formula. Think of this as the square of a sum. Okay, so a plus b is a sum, and then, the squared power, this is a sum squared, or the square of a sum. Call this formula, in your notes, in your justifications, in your proofs, by the square of a sum identity. The square of a sum is this. Heck yeah, dude. Yeah, I know this just because it was taught, but understanding it like this is great in a more proof-based context. Yeah, we're all so used to, like, we all memorize the patterns, and we've seen things like 12 plus 34 times, whatever, dude, 56 plus 78, right? Like, I'm just using 1, 2, 3, 4, 5, 6, 7, 8 to make up a problem. We're used to foiling a problem like this. Technically, I haven't shown foiling. I've shown... Technically, so far, we've only shown this. 12 plus 34 times 12 plus 34 is 12 squared plus 2 times 12 times 34 plus 34 squared, right? So we're used to using this fact, or in general, for 4 different terms, a plus b times c plus d, first, outer, inner, last, ac plus ad plus bc plus bd. Like, we were all taught this. You multiply that one with that one, that one with that one, this one with this one, and this one with this one. And we call this foiling. Really, this is just a double distributivity. Yeah, FOIL is 2 distributivities. It's just a double distributivity. It's distributivity on steroids. And what's super cool is that we showed this formula, but you can prove FOIL for yourself, and it's almost the exact same proof. It's almost the exact same proof to prove and understand why FOIL works. When am I streaming? I'm streaming almost every day. So, dude, great to see you. Great to meet you. Let me write down your name. Dude, thank you so much for supporting my journey. Jack Mac 8715. You are the first supporter of section 3. Jack Mac 8715. Thank you for letting me explain distributivity to you, dude. You're right there. Appreciate you, man. Got a dip, class starting. See you soon. See you later, man. Enjoy class. All right, let's get back to the representation theory. Oh, wait, no, this was chapter... We switched to the other thingamabob. Let's get back to grad... I should probably wrap this up. We're at about 3 hours now. Did we get to 30 likes? Do I owe you all push-ups? Yeah, nobody told me. You all are supposed to tell me. When we get to 30 likes, I'll do another 10 push-ups. Y'all, I'm having fun. I'm learning a little bit of category theory. I think, like, we're starting to get closer to category theory, which makes me very excited. Thank you, everybody, for watching. I had fun today. Let's go. 10 push-ups. I'll play a song. I don't know. I kind of want to stream guitar. I think I could stream some guitar. Yeah, we might stream some guitar. All right. Thank you, everybody, for being here. Yeah, dude. There's 10 push-ups. Let me set up my stream. It's been a while. I've been neglecting my guitar audience. So for those who don't know, I am also a classical guitar practice streamer, and today I would like to share some classical guitar practice with anybody who might want to cross over and check out what that would be like. It's meant to be like a chill, nice study with me kind of setting as well. Like some people don't even like classical guitar that much, or they're definitely not classical guitarists themselves. Like some of the super regulars who show up all the time are not even classical guitarists at all, but they like to just hang out and vibe. So I hope you join us for the raid. I'm going to raid myself because I'm very selfish. So see you there. I'll play a song real quick before we cross over. Yo, which Discord server? You're starting a category theory lecture series in a Discord server this weekend. That's awesome. I am interested, but I don't want to. Oh, Math with Ming is live. Oh, we could raid Math with Ming. Yeah, let's do that. If he's live, let me know. I will hang out for a little bit there. Let's raid Math with Ming, and then I will be streaming some classical guitar. Hell yeah, dude. That's awesome. Yeah, let's do that. Vimothy Vestibule. Okay, interesting. Here's a chance for anybody who's not already in my Discord. Please do join. We'd love to have you. We've got a few people who are, category theory fanatics. Locke is in there. Leo's in there. It's currently doing vector algebra. Ugh. Don't you hate that? Don't you, you're about geometric algebra, right? Thank you. Thank you for the link. I was just going to set that up. Customization. Yeah, man, let's go say hi. I have not caught his... What? I don't see it. I think he doesn't have rating turned on. Nobody knows about it. I swear, dude, nobody knows that you can do this. YouTube makes it so damn hard. It's so annoying. Oh wait. Maybe I pasted the wrong thing. Never mind. Let me try one more time. Yep. He doesn't have redirecting on. Yeah, nobody knows that you can do this. Nobody does it on YouTube. Literally nobody does this on YouTube, dude. Redirect privilege is needed. Ask Math with Ming to add you to their live redirect list in community settings. Okay, we will have to do that. Okay, so everybody join us. Rating after party at Math with Ming's stream. Say JC after party. Or JC practices after party. So everybody say that if you're joining us. Thank you everybody for watching. I'm looking forward to this. I have not met him yet. Cool. So here is the link. Awesome. See you there, everybody. Thanks for watching. Bye. Bye. And then I'll be maybe streaming guitar.